get sound and video synchronized. Now, today's lab demonstration is entitled Formation Constant for the Complex Ion Silver Diammonia plus 1. A discussion of the theory behind this and the manipulations, the formations of the equations is right here in the method, and it's very detailed. If that's not enough, then I have another video that will be posted along with this one that will give you up close and personal. But the summation of all of these manipulations gives us a formula here. Kf equals the complex ion concentration times the chloride concentration divided by the ammonia concentration squared times the solubility product of silver chloride. All right, so what does that mean? That means that first, we're going to use all of these reagents and this equipment to produce a complex ion. We are actually going to produce the silver diammonia complex ion in different concentrations, one for each here. And then we're going to titrate that solution with a known concentration of potassium chloride. The potassium is a spectator. The reaction takes place between the chlorine and the silver that is part of the complex ion. But as you know, whenever you have a even a solid precipitate in a solution or a complex ion which is not precipitated, there's an equilibrium between in one case, the silver chloride and the silver ions and the chloride ions in solution. And there's also, in that same environment, the way we've set it up, there is an equilibrium between free silver ions, free ammonia molecules, and the complex ion. Now, since both of them are together in the same solution, if we titrate the solution against the potassium chloride, and right at the point that the silver chloride forms and precipitates is our endpoint. And this formation constant formula here that we've developed, it's in the blue box on your method, right? There's your method. And in that blue box over here, that's the formula that we use to do the calculations. So the real trick, this is not a difficult experiment, but the trick is manipulating the numbers afterwards to get the answer. So that's why you need to be thoroughly familiar with the method and the mathematics that go along with the calculations before you can understand what's happening. In fact, I've even got a sample problem right here. You can see it on my head cam. A sample problem worked out here in detail to guide you through the process. All right. So let's look at the method and proceed. I've got on the board over there, I've got a table set up to input the information, and then I'll scan it with the head cam so you can be easier to see than putting things here on this sheet of paper. It'd be too small to see. All right, so what do we need to do? Well, it's been my experience. Initially, the method was set up for 4 different concentrations of silver against ammonia. And that changes the equilibrium expression for the silver diammonia complex ion. But what I discovered the hard way, and my class with me, is that the higher concentrations of ammonia are extremely difficult to get accurate results. And the only reliable results that we've been able to manage so far are with the very lowest concentration of ammonia. So in this method, that would be 5 milliliters of the silver nitrate solution mixed with 5 milliliters of the ammonia solution. We could, if we have time today, we could do a 5 milliliter and a 10 milliliter. But the titration is difficult and the outcome is pretty iffy. So I'm definitely going to do the first one, the lowest concentration, and we'll see what happens. Okay, I will say that while we're titrating, how do you know where the endpoint is? Well, I mentioned earlier, the endpoint is where the silver chloride forms and remains persistent. The method originally said, look for a persistent opalescence. So silver chloride would sort of reflect light. But it's difficult to see that in a brightly lit laboratory environment. So what we use here to detect the presence of a precipitate is the Tyndall effect. The Tyndall effect was named after Tyndall, and it was used to discover the difference between a solution and a suspension. When you have a suspension that we're looking for, the silver chloride is suspended in the matrix, and if you shine a bright light through it, see, through the mixture, you will see the light beam because the suspended particles are diffracting the signal, the light. If it's a solution, then the light will go through the solution, out the other side, and you can catch the beam on the other side, but you won't see it in the solution. So in order to do that and accurately detect it, I have to dim the lights. So that's another problem. The video may not pick up all of the things, so I'll continue to narrate as we go. All right, so there's my light, and we need to make the solution, okay? So the first solution, we need a 0.1 molar silver nitrate solution, and I just prepared that fresh this morning. We also need a 1 molar ammonia solution, and the exact concentration needs to be known. 0.1 molar, 0.1000 molar silver nitrate is here. And then this one was determined to be 1.0416 molar. So it's just a little over, but you need that exact value. And I've written it on the board, so you'll catch it in the video. And we're going to combine those two to make our solution before we titrate it. Okay, so what do we need? Well, we need a 100 milliliter volumetric flask. So there's a mark on it right here. And that tells you that you have exactly 100 milliliters of solution or liquid in here. And this is plus or minus 0.08 milliliters. So it's very, very accurate. Okay, we got that. We need a way to measure out each one of these. And there's going to be 5 milliliters of each one, but we don't want to cross-contaminate. So we have two 5 milliliter volumetric pipettes, one for each. And we also have a pipette bulb, and you're familiar with this item, so I don't have to explain how to use it. We've used it several times before, both in Gen Chem 1 and in a previous lab in this course. So that's what I'm going to do first. I'm going to prepare that solution using 5 milliliters each of the two solutions and put them in here and dilute it to the volume. So let me get on with it. Remember, we need chem wipes. We're going to do the silver first. All right. We need to prime the bulb. All right, there it is. And we need to open the container. And notice I have silver nitrate in an amber bottle. Silver will become reduced in the presence of light. So it's very sensitive to light. In fact, silver reaction to light is the whole basis for modern photography. Well, before we had CCDs in our cameras. When we had film in the cameras, yeah, silver was the basis. Okay, so let's prepare by sucking up first. 5, we're going to make, eventually we're going to have 5 milliliters in this pipette, and we're going to dispense it into the 100 milliliter volumetric flask. So remember, you wipe down the tip, and then you expel down to the mark. See, I'll tilt my head back. Maybe you can see it a little bit better with my head cam. Here we go. Almost. Right there. Touch the tip, get those drops off of there, and then dispense. And you just wait for gravity to do its thing. Let's see. I'll shift this with my foot just a little bit. There you go. Almost drifting off camera. Okay. And then the last thing you do is touch the tip to the inside, and we're done with the silver. Okay. Set that aside and clean it up later. Or we might use it later. So we'll keep them together. Right. We might prepare the stronger solution if there's time. Now we need ammonia, 5 milliliters. Go, like that. And now we suck it up in our volumetric pipette. There we go. Wipe off the tip. Let's see. That's ammonia, all right. If you were asleep, you'll be awake now. And then we bring it down to the mark. There we go. I can see it. I have to get my eye level with the mark, and there it is. Okay. Expel that. Just let it drain. These pipettes are calibrated with aqueous solutions, so let them drain under gravity. And now we touch the tip, and that one's done. So we're going to seal this up. There we go. Set it aside with the pipette separated, so we might need to use them again. Well, actually, we won't use the 5 milliliter ammonia again. The next time we use it, if we do, is 10 milliliters. All right. So there we have both solutions, but we need to dilute it to 100 milliliters. So I need wash bottle with distilled water. Wash down the sides for sure. And be sure everything is in the bottom before we bring it to volume. And then periodically we mix it. If this were a larger flask, I'd use the supply bottle and then finish it off with the wash bottle. But since it's only 100 milliliters, I can afford to squeeze. And then what you're supposed to do when you get to the mark is, let's see, let's mix it one more time. Okay, once we get close to the mark, the ideal situation is rather than do it freehand, set it on the bench and take your eye to that level. Make sure that your eye is level with the mark and then finish it off. This takes some practice because there's water draining down the inside, so you don't want to bring it right up to the mark with the bottle because then it'll drain some more and be above the mark. So you're careful and you do it in increments. And there, I'm right on the mark. It's finished draining. Okay. Now, hold that cap in there tight. This stopper. And be sure it's well mixed. Okay. Now, in this solution, we have actually formed the complex ion. And it is in equilibrium with the solution, in equilibrium with the silver ions and ammonia left in solution. So there is an equilibrium there, and we're going to titrate that silver that is still in solution. But while we're titrating it, we have to add enough chlorine, enough chloride ion, for it to exceed the solubility product of silver chloride. Otherwise, we won't see it. So we're using 2 equilibria to answer a question about one of them. So there you go. There's the solution. I better mark that. I think I got a marker in here. Yeah. I better mark this one as the, I'll just mark it number 1 because we're going from low to high. In case we do the other one, then I won't get it confused with the next preparation. Okay, so now we've prepared the solution. Okay, and we transfer the entire contents, 100 milliliters, to an Erlenmeyer flask. So this Erlenmeyer flask is 125 milliliter flask. Of course, it's closer to 150 milliliters at the top. So 100 milliliters will bring it about right here. Okay, so there's room to add titrant to it. Okay. So I'm not going to pour it over yet. Well, I want to prepare this. I know the method says pour that into your Erlenmeyer flask, but I want to prepare the burette first, okay? Just to be safe, because this is not going to have a lid on it, and this one does have a lid. So we'll set those aside, and we'll prepare this sort of out of order, and we'll fill this one with 0.1 molar potassium chloride. Here it is. This is actually 0.100 molar potassium chloride. So if that's the molarity of potassium chloride, what's the molarity of the chloride ion in here? It's the same, right? If the compound is 0.1 molar and the ratio is 1K per 1 Cl, then when they divide, when they ionize in water, they're separated. Potassium plus K plus ion and Cl minus ion, each one of those is also 0.1 molar. So actually, this is 0.1 molar chloride ion. Okay, so we need to fill up the burette, and we do it with a similar method that we've done before with our acid-base titrations and determining the molar mass of an acid by titration. The solution we add in our burette, we follow a similar procedure. So I'll try to narrate as I go, of course, but we're going to need a funnel. Right? And actually, it might be safer if I get a beaker. So I'm going to get a beaker here. This is a good size. Because a beaker gives me better control of addition. I'm going to bring this down a little bit so I can reach the top easier. And we'll reposition it later. Right. Remember, your burette starts off with a loosened stopcock. So you need to tighten it up, and I've already done that. And you run the handle perpendicular to the direction of the burette. That is closed, right? You don't want to turn it parallel. It's open. When you pour stuff in there, it's just going to come out on the lab bench. So perpendicular is closed, and now it's ready to receive the first rinse. So I'm going to take this 0.1 molar KCl. Let's see, maybe the camera can see it better, my head camera. And I'm going to put a little bit over here in this clean beaker. Okay. And then we're going to rinse out our burette. Oops. I need my funnel. We only have to add a few milliliters. That's plenty. That's more than enough. Kind of overdid it there. And then, remember what I said, if your gloved hand is clean, which this is, then you can just cup the end of it and rock it and rotate and rock it and rotate. And we have rinsed out the inside of our burette. Okay. So now we're going to drain it out. There's one other thing I forgot. Right? What did I forget? My waste beaker. All right, so here's my waste beaker. We're going to mark it. Go. Now, we're just going to let it drain. And while it's draining, I'm going to check my camera battery, okay? Because I don't trust this thing. It runs out quickly. So let's stop the video because the battery indicator is not accurate unless you stop the video. Okay, we're still good. So now I'm going to start it up again. Record. Here we go. Put it back on my head. Now I need to do another sound synchronization. So you get to watch me clap my hands. I can see it from both of them. All right. So there we are. And off the tip. Now we want to fill it up. So let's put the funnel back in it. I think we're going to have time to do one titration because they're going to kick me out of here in an hour and a half. So we'll just be sure we get that one set of data. So let's that. All right. 0.1 molar KCl. Now we're going to fill it up past the 0 mark. Okay. More. Uh-oh. It's draining because I left the stopcock open. Imagine that. I'll tell you why that was not a completely bad thing in just a second. Here we go. All right. So why was that not a bad thing? Well, remember on previous titrations, I mentioned you got to get rid of any air bubbles in the tip of your burette. That burette was open, so it was blowing through there with maximum force and speed, and it blew out any air bubbles that were left. So I wasted some reagent, yes, but I got rid of the air bubbles. So that step is done for me. It's ready to go, except I need to bring this back down to 0. I want to start on 0 so that whatever the volume I read here is the volume dispensed. Remember, burettes are start at 0 and go with high numbers down because they're giving you the volume that is dispensed, not the volume that's contained. Okay, so let me delicately bring it down. Got my eye level with the 0 mark, and we're coming down. And let's slow it down a little bit and let it drip slowly. So I want to be right on the mark. There it is. My meniscus, the bottom of my meniscus is right on the 0 mark now. There we go. Now we can do the titration. So I need to dispense the 100 milliliters of solution that we prepared earlier into this flask. Here we go. And I want to put a stir bar in it, magnetic stir bar, because this is a magnetic stir. You've seen me use this before. It's a Teflon coated magnet. And what it does is it constantly stirs the solution. You don't want to go so fast that you have a vortex in the middle, because that makes it difficult to see the light beam. So I'm going to turn it like this. Now I can see without the interference of the lettering that's on the flask. I think I'll go a little faster. There we go. Just starting to form a little dimple in the top. Now what I have to do, since it's set on 0, now what I have to do is I have to dim the lights. So I'm going to dim the lights and see what effect that has on the recording. Unfortunately, it might not. You will definitely be able to see the light beam, right? And I think I'll turn it this way. I know that's a long way from that camera, but maybe with my head cam, you can see the light beam as we approach the end point. Okay, so now I'm going to dim the lights. Okay, it looks like we're still picking something up. So hopefully we'll be able to see, notice, well, maybe you can notice, maybe you can't. But with my head cam, I hope you can see that you cannot see the light beam in the solution, right? That says that we do have a solution, right? There are no suspended particles in there. So we're going to start adding. And we're going to add slowly. Let me do the light beam on this side so I can adjust this with my right hand. Okay, so I'm going to start off really slowly because I can't remember exactly how much volume it takes. Okay, I think I can see it. I don't know if you can. I can see the formation of silver chloride. It's slowly Okay, now it's gone, right? We performed a Le Chatelier on it. We disturbed the equilibrium and produced some silver chloride temporarily. Now the silver chloride is gone because equilibrium is reestablished. So let me put another drop in. There we go. Let's pick it up a little bit. Looks like it could stand a little more speed. Mixing. There we go. See, it's gone. Now, when we get to the point where that precipitate is permanent, but just at the very point when it first appears and stays, that's the endpoint. So let's put another drop. There we go. I hope you can see this because it's beautiful. Another drop. It forms and there it goes. This might take a while if I do it this slow, but I'm not too sure how much of this I need to put in there to reach the endpoint. Maybe I can save some time by looking at a previous. Let me do that. I'm going to leave this for just a second and check my records and see if I can get close to it and save us some time. Let's see here. It says it's close to 1 milliliter of the potassium chloride. Let's see where it is now. Oh, it's a long way. So let's bring it down. Let me go down to 0.5 ml. There. Okay, you can see the light beam now, but does it disappear? Yeah, it's gone. Okay, so let's dispense a little bit more. Maybe 3/4 of a mil. Don't want to go past the endpoint. There we go. Yeah, you can see it. You can see the light beam right straight across there. Tilt my head back, maybe you can see it better. Come down, so maybe the camera will catch it better. You can still see it. I hope I didn't overshoot it. Okay, you can see it better that way. Keep going, keep going. It's just my luck if we overshot. You know, I may have. Shoot, that's disappointing. Check my watch. Do I have time enough to do another one? Yeah, if I hurry. I think I did. I think I overshot. Okay, so let's read this volume and we'll just record it. I mean, we went to the trouble, we might as well write it down. So how much did we add? Yeah, it's still there. How much did we add? Let me put a white sheet behind. There we go. So I see 0.65. Okay, we're going to have to make another solution. Let me turn the lights on so I see what I'm doing. Now, I'm not going to narrate this one because I'm interested in getting this thing done in a hurry. So here's the original. We can reuse this one, but we do have to rinse it out. Okay. There's not enough ammonia or silver in there to be of concern. So that goes down the drain. And we need to clean off the stopper. There we go. Now we're going to go back and make up solution with 5 milliliters of silver. You see me? Yeah, I'm still there. All right. I wasn't paying attention. Go. And down to the mark right there. All right. So now we need 5 milliliters of ammonia. Something too far. Back it up. There we go. Okay. Right on the mark. Oh, what is that doing? Oh, okay. I saw a little reaction there before it reached equilibrium. Okay. Now we need to rinse it down. I think I will use the dispenser over here. Here we go. Now we can finish it off to the mark. Let's see, I was going to do it the unkosher way. Let's do it. Sit it on the bench, bring it up to the mark. A little more. There it is. Right on the money. Mix it. Let's try this again. This time get it right. Let me see if I can see without the. And it's still there. Okay. So let's turn this stirring machine off. Let's go up a little bit. There we go. Let's extract our stir bar and rinse it off. Go. Now we need another 125 milliliter Erlenmeyer flask. Go. And transfer. There we go. Now we'll put the stir bar back in it. And I'll tell you what. Let's set this, let me bring it down to 1 milliliter. Exactly on the 1 milliliter mark. That way, all I have to do is subtract 1 milliliter from the value I get. So let's bring it down to 1 mil. Oh, too far. I have to go down to 2. And there. Okay, so now we're primed and ready to go again. So I'll do that subtraction in my head. When I say we've got a 1/2 mil delivered, I've already made the calculation in my head. All right, let's drop this down and start to stir. Oops, too much. Back it off a little. There we go. Now I'm going to cut the lights again. Now I believe the last time we were safe down to a 1/2 milliliter. So I should be able to add a 1/2 milliliter without overshooting. So that's what I'm going to do. All right, so here we go. There's a 1/2 mil. That's known as magnetic decoupling. When the stir bar starts jumping around. Let's reestablish the couple and then we'll go ahead. Oh yeah, slow is plenty fast. Okay, now we're going to add drop at a time, like we did before. You watch the tip and see the drop form. There you go. See it hit the water, hit the solution, change. Okay, is it going to go away? Still working on it. You can see it from this angle. Yeah, there we go, it's gone. Now what I'm seeing is reflection on the glass. I'm not seeing the light beam. Okay. Hope you can see it from there. I know it's probably not. The head cam hopefully will get it. Let's add another drop. One more drop coming up. One more drop. Come on, come on. Very sensitive. There we go. Okay, we formed the silver chloride, disturbed the equilibrium. Now it's reestablishing. And when we reach the end point, the equilibrium then will include silver chloride in the solid form. Right now, there's none because the silver ammonia complex has consumed it. Well, we formed the silver chloride first with the addition of chloride, and then the equilibrium shifted back toward the complex ion. So what we want to do is catch it right at point where it does that. Okay, you add a little more. What's it going to do? It's consuming it. All right. Let's see, can I see the light beam? Not anymore. It's gone. So let's try another one. There it is. Come on, there you go. Notice I tapped the tip. That makes sure that the drop that fell off is all that was delivered. And we didn't have anything clinging on the tip. Okay, I can see the light beam still. It's fading, fading, gone. Let's add another drop. There we go. You can see the light beam. I can see the light beam. I hope the camera catches it. This is the first time I've ever recorded this particular procedure, so I'm not sure how well the camera's going to show it. That's why I'm taking pains to narrate. What do I see? There we go. That's a better one. I can see the light beam very clearly. It's still there. We might have it. This might be the end point. Let's give it a minute or two, see if it fades anymore. If the opalescence persists, if the Tyndall effect is seen, it does not go away, and I'll rock the beam so you can see it moving up and down, hopefully. I think we might be there. Yeah, it should have been gone by now, I would think. So let me take a reading. And that'll take a few seconds, and then we'll come back and check to be sure. To be sure that the silver chloride is still there. So let me read it. You know, the background. This might work better. I don't even like it. So this is 0.567, right on the money. 0.70. Okay. Before it was 0.65. 0.70. Let's check it again. Yep, you can still see the light beam. See, I'm rocking it up and down. Hopefully the camera catches it. Yep, so we can average those values actually. 0.675, 0.675 we'll use as our value. Yeah, that's probably not fair. 0.65, we thought we might have overshot. Let's use 0.7. We just go with 0.7 milliliters. Okay, let me turn the lights back on, and then we'll record our data and see what else we have to learn from this procedure. Okay, I think we're done here. Turn it off. Oops, we're gonna have to move this up some. There we go. Now, I'm gonna leave that there for now so we can finish this up and I can close the video out, and then I'll just do a cleanup. All right, so I'm gonna have to leave this camera and go to the board and rely on the head cam to finish. But before I do, I want to check the battery because I don't want it to go out in the middle. So let's do that. Okay. I'm going to stop it. In fact, I'm going to turn it off and replace the battery. Then my conscience is clear. So let's take the power down. There we go. And you can watch me change the battery if I leave this in the video. So we open the bottom, pull this battery out, and stick it in the charger. And put a fresh one in. That's really hot though. Why it's doing that? There we go. Put this back in the headgear. There we go. Turn it back on. And start the recording. Okay, so this is a good break point. We've finished the actual lab effort, and now we're going to go to how to treat the data. All right, so I'm going to tilt this camera up just a hair. Not too much. So we'll see the board a little better.
All right, so now we're on the mobile cam. And what we have over here, let me tilt my head back so you can see it. Here we have identified the Chem104 or CH214 because I'm going to make this video available to 2 different courses at 2 different schools. This is the information that's given. The accepted value for the formation constant of this ion is that value. So what we need is an expression of the formation constant. We need the equation for that. So I'll do that in just a minute. Then we're going to need the solubility product, KSP, for silver chloride, which is this value, right? This is the accepted value for the one that we're going to determine. So we compare the one that we determine to this one. This is given. This is the concentration of silver nitrate. This is the concentration of the ammonia, right? So there you have all your information right there, and I'll stop for a second, tilt my head one way and the other to be sure it's on camera. And then over here, we need to put in the volume, right? So I remember what the volume was. We decided to settle on 0.70 milliliters. And we're not going to do this one. So this experiment, the way we did it, has no replicates. It's just a single determination. And of course, if you were going to do this for a research project, you would do it many times. Okay, so here's the volume of silver nitrate that we added. Here's the volume of 1 molar ammonia that we added. Here's the volume that these two were diluted to in the flask. And then we added some to it, right, when we titrated with potassium chloride. So the total volume, which we need to know later, the total volume is 100.70 milliliters. We can do this. That's okay. To be sure that we have everything included. Okay. So now, the expression for the formation constant is the free silver ions and the free ammonia yields that. So it looks like this. Silver in solution, right? We added it as silver nitrate. Silver in solution plus 2 moles for every 1 of ammonia in solution. Okay? And this is in equilibrium with that complex ion. Okay? Notice the charge is the same on both sides, a plus here and a plus there. And it takes 2 moles of ammonia to form this complex ion. It actually does it in steps. First, it forms an ion with just ammonia, but the equilibrium shifts it immediately to add another ammonia. And this is where it stops. So the composite is this one, and the Kf is for that expression. All right? So what does that expression look like? Well, the Kf would be, the same equilibrium rules apply. It's the product divided by, it's the product of the reaction divided by the product, the mathematical product of the concentration of silver divided by the concentration of ammonia squared. Okay? So this expression is going to look like this. Kf equals the equilibrium concentration of the complex ion, like that, divided by the silver ion concentration times the ammonia concentration squared. So that's what the Kf is. But it's difficult to determine, to find an endpoint for this reaction, for what do we titrate it with? You know? So we have to get at this value indirectly. That's where we use this expression for titration. So we're going to have the KSP for silver chloride, right? That was the opalescent color, is in equilibrium with silver ions and chloride ions. Both of these reactions are occurring simultaneously in the same reaction vessel. So this KSP for that reaction is equal to, right, this is a solid, so it's not part of the expression. It's just these two. Like that. Okay? So now, how do we combine these two? Well, what do we have in these two expressions that is common to both? The silver ion. That's the only thing that is common to both of them. So if we solve this for silver, there, we can substitute this expression right here in here. Okay? And that's what the that's what this blue box down here shows you. After you substitute that in here, this is what you get right here. So it's going to look like this. The formation constant then, with our titration involved, is silver diammonia ion concentration and the chloride ion concentration divided by like that. Okay. Now we still have a problem, because how do we use this information? This will give us the calculation, but how do we get at these concentrations? Right? So that's what we have right here. Right? This part right here. we've got this expression, but we can't use the KSP in the expression because the titration used concentrations of various components, and the KSP wasn't one of them. So what we need, and what I'm getting at is, we need to find a way to augment this equation such that we can produce another equilibrium expression and build an ICE table. Remember, initial, change, equilibrium. Build an ICE table. So in order to do that, we've got to substitute back in here what is KSP equal to. KSP is equal to silver times chloride. Okay. Now, if we if we back figure from this expression, what would the equation look like? Right? This would be on the product side, and this would be on the reactant side. So our table would look like this. We would have this on the product side. We're going to do the reactant side first. So what we would have is, we would have silver. I'll do a little out of order. And then we would have ammonia. And then we would have chloride on this side of the equation. Right? And then on the other side, we would have the complex ion. And sorry, I'm going to have to erase this. Plus chloride ion. Now when we build our ICE table, we have concentrations for each one at various steps. So initially, we have something, then the change, and then the equilibrium, right? So that was the first trick. The next trick is, rather than put concentration values in here in the beginning, we're going to use absolute values. And then afterwards, once we find out what the equilibrium absolute values are, we'll calculate the concentrations. And then the concentrations can go into our expression. Right here. No, not that one. The one I erased. Sorry. Where we have KSP right here. And then we can put in these values because this is after the reaction. This is before the reaction. Okay. So in your example, the values for the absolute amounts are in millimoles. Now, why do I use millimoles? For convenience. If you multiply the molarity times the milliliter, you get the millimoles, right? If you multiply molarity times liters, you get moles. But we're going to use millimoles because of this relationship. Molarity is equal to moles per liter. It's also equal to millimoles per milliliter. Now, take a close look at that. Moles per liter is by definition. If we take a milli of this one and a milli of that one, we haven't changed anything. It's like we divide this one by 1,000, divide that one by 1,000. The ratio is still the same. So that's why it's more convenient to use millimoles and milliliters when we do these calculations. That saves us a step. We don't have to convert and run the risk of making an error. So we just use milli everything. Okay, so what's the initial number of millimoles of silver ions? Right here. 0.1 times 5 is 0.5 millimoles. Millimoles. What's the amount of ammonia? Well, 5 times 1.046, I need to get my calculator, don't I? Let's see how I'm doing on time. I may have to cut this short because they're going to kick me out of here in a half an hour. Okay, so 1.0416 times 5 is 5.208. So 5.208 millimoles. Okay? That's our starting concentration. How about the chloride? What's the starting amount of chloride? Well, let's see. Here. Remember I said milliliters, actually the same moles of this is the moles of chloride. So if we find the millimoles of that, it's equal to the millimoles of chloride. So 0.7 times 0.1 is 0.07. 0.070, that's good enough, millimoles. That's what you start with. Now, what do you have over here when you start with that? Well, like any of our expressions, you start with 0 here, millimoles. And you start with 0 here. All right? Now, what's the change? Well, the change is, during the reaction, we use up all the chloride. All of it goes from reactant to product. Right? So this is going to be minus 0.070, and this is going to be plus 0.070 millimoles. Okay? That's the easy one. How about this one? Well, we have to go back here. In this one, we're going to use all of this up in the reaction and produce that side. So this is, we subtract all of this, and of course that leaves us 0 here, and that leaves us 0 here. But how much ammonia did we use? Well, what's the ratio? Right? For every one of these, you use 2 of those. So for every one of these, we subtracted 2 of these, minus 1.000. So now we have 4.208 millimoles of ammonia left. And on this side, we have, right, 1 here, 1 there, equal molar ratio. So if we subtract a half a mole on that side, we end up with 0.500 on this side, which gives us that. Okay? And of course over here, we added this one on this side, which is 0.070 millimoles. Okay? I hope you're following this. Let's see, that's kind of unclear. Let's make that There we go. So now, at equilibrium, we have these concentrations, right? So for our equilibrium expression, we know what this is. We know what this is, right? We know what ammonia is left over, and we know the KSP, because that's what this is. And we can calculate KF, except we don't have concentrations yet, right? So what is the concentration of each one of these, right? It's millimoles divided by milliliters. So how many milliliters do we have in that vessel when we finish titration? Right here. 100.70 milliliters. So each one of these is divided by 100.70 milliliters. Each one. Okay? Now that will give you molar concentration of each one. And then all you have to do is plug it 1, 2, 3, KSP, calculate. So there I have, worked the problem for you. So if you can't write a report, since I did the work for you, then you're in pretty sad shape. What I want you to do is understand what has happened. That's why I went to all that detail, explaining everything. Okay, so let me take a slow. I'll tilt my head back to be sure that everything is in scene for this part. Then I'll move over. Everything is in scene there, except for the part that I erased. I apologize for that. And then this side. So we got everything we need to finish the report. All right. So let me see here. Is there anything else I need to do before I shut this thing down? I think all I have left is the cleanup. And this one is still recording, so you probably heard me yammering over there next to the board. Okay. So I think we can shut this down, and that is formation constant for the complex ion, silver diammonia +1.